Welcome everyone. My name is Garmendia and I will present a paper titled Automated Variability Injection for Graphical Modeling Languages. This is a joint work with Manuel, Wimmer, Esther, Guerra, Elena, Gómez-Martínez and Juan de Lara. So let's start. In this presentation I will introduce the concept of variability in production systems and the technical cost that implies the combination of software product lines and model-driven engineering. After this, I'm going to present our approach to mitigate this problem, using PetriNet as a running example. Then, I will introduce the tool that we implemented called Verso, and finally a summary and future work. Model-driven engineering promotes models as the main artifact of the development process. In MDE, models are used to specify, test, simulate, analyze, and generate code for the final application, among other activities. This model focuses on the essential aspect of the system to be built and are created using modeling languages. The modeling languages comprise abstract syntax, concrete syntax, and semantics. In MDE, the abstract syntax is defined via a metamodel, typically expressed as a class diagram with OCL constraints. Regarding their syntax, DSLs can broadly be classified as textual or graphical. In this presentation, we will focus on graphical representations. Despite MDE has proven to be especially effective in narrow domains, it may fall short to handle a potentially large family of systems. In such cases, one can resort to software product line techniques to avoid modeling explicitly each system of the family. For instance, this is a metamodel that describes a PetriNet language. Over the years, the basis of this language remains the same, but some type of PetriNets have been introduced, like the addition of marking that can be stored directly in a place or a token object. Software product lines permit specifying variation points on a given model, and hence elude the exponential cost of specifying each model variant separately. However, its technical cost is high, because it requires modifying, extending many MDE artifacts like the metamodel and the graphical editor. So to explain our approach, I'm going to use PetriNet models, due to the rich body of theoretical results for simulation and analysis. However, while we have a graphical editor for PetriNet's modeling, the editor doesn't permit specifying variability as required in this scenario. Modifying this editor by hand to support the definition of PetriNet with variability would be costly, as we would need to extend the PetriNet language, modify the editor to allow specifying the variants, and finally develop an environment. As a summary, our work aims at automating this task. So let's see how to define a graphical DSL in MDE. In MDE, we usually define first a metamodel. In this case, we show the metamodel for the PetriNet language, which contain classes to represent places, transitions, tokens, and direct arcs between places and transitions, and vice versa. A container class PetriNet groups the elements belonging to the same net. Places, transitions, and arc have a name, while places have a marking represented by container tokens. Below the metamodel definition, it is shown a model that is an instance of this metamodel. The model contains one place that is connected to a transition and has one token. On the right side of the metamodel, it is defined an excerpt of the graphical syntax definition for PetriNet. This is a typical approach to specify the graphical syntax for a modeling languages, which is by establishing mappings between its metamodel elements and graphical primitives. This way, the concrete syntax definition assigns a diagram description to the root class of the metamodel, in this case PetriNet, and a black square to transition, labeled with the transition's name. Below this excerpt, it is depicted a model using the defined concrete syntax. To model the variability space of a family of models, our proposed approach relies on the use of feature diagrams. This figure depicts the feature diagram for our example assembly line. It defines the features that a model of the family may have, part A, part B, quality control, etc., and how they can be combined to obtain a valid feature configuration. A valid configuration requires choosing at least one of part A and part B, while quality control on parallel can be selected or not. Overall, this feature diagrams allows 12 valid feature configurations for the assembly line. Our proposal follows an annotative approach to define a model family. Specifically, a model family is represented by a so-called 150% model that contains all the elements that may appear in models of the family. Such elements may be annotated with present conditions, that is a logic formula over the feature defined in the feature diagram. On the right side of the feature diagram, it is depicted an example. We enclose the elements with a present condition using a dashed region. The bottom figure shows the product PretriNet that results for selecting features part B, parallel, in parts, process, and flexible assembly line, and discarding part A and quality control. Please note that when we deleted one object, we deleted its input-output references as well. Then, we have to take into account a couple of aspects when designing the variability on the abstract syntax. Designing the variability for a DSL basically requires considering two aspects. Firstly, deciding which elements can be subject to variability, and secondly, there may be the need to specify well-formed rules among the present conditions of different elements. These rules must be taken into account in order to ensure the generation of consistent models. The first rule is the restriction for composition. For instance, if token would not be allowed to have present conditions like in this figure, but the container places are, then we could end up generating products where token objects would be outside of their containers. Then, to avoid this, we force that if place is present condition enabled, so must be token. This avoids producing models where the instances of tokens lose its container object, in this case, place. The second rule that may be specified is the predicated stronger than, to require the present condition of any instance of class A to be stronger than the present condition of any instance of class B, reachable via a reference, where the reference can go from A to B. In this case, we configure PTR to have a stronger present condition than place. This disallows a variability specification like this one, that leads to a product where the minimum cardinality constraint input would be violated. So knowing these rules, let's see how we can define this specification on the PretriNet metamodel. The figure shows the variability inscription on our example metamodel. Two classes are enabled to have presence conditions, element and token. Consequently, all concrete classes of element become present condition enabled, as well PTArg, TPR, place and transitions. Since both place and token are present condition enabled, and there is a composition relation between them, the present condition of the instances of token will be conjoined with the present condition of the container place. This avoids tokens outside places. PretriNet instances are not allowed to have variability. Finally, predicate stronger than is used 4 times to ensure that the present condition of the arc, either PTArg or TPArg, is stronger than the input-output place transition. These predicates are added automatically to avoid arcs with undefined input or output in product nets. Given the language metamodel with the variability inscription and a specification of the concrete syntax, our approach adapts the latter to permit a relation between the graphical representation of a present condition and the model elements that may be subject to it. The present conditions are specified in the dedicated layer added to the concrete syntax and provide a palette for creating present condition and a textual editor for their editing. The present condition abstract syntax model is serialized separately from the language model. The cross references from the present condition to the model elements are based on the element's ID or name. So we have built an Eclipse plugin called Perso, which is available at this address. With this tool, we are able to automatically adapt existing graphical Sirius editors to allow the definition of model with variability. We use Sirius since it is widely used within Eclipse. The main component of Perso is its editor, which receives a model with the concrete syntax definition of an existing Sirius editor as input, with the extension or design. Then, the editor permits configuring the classes that can have a present condition attached and defining a stronger than predicates. This information is back-propagated to the metamodel with the abstract syntax definition. From this information, Verso extends the editor with the present condition layer that is used to store the present condition of the models being edited, and can be deactivated on demand to hide or show the present conditions. Moreover, the adapted graphical editor integrates a textual editor that permits defining present condition textually, and provides code completion and feature name resolution. In addition, Verso generates a feature ID plugin which supports the specification of feature model, selecting configuration and producing the corresponding product models. For this purpose, an automatically generated composer synthesizes the appropriate product model given a 150% model and a configuration. Let's see how our tool works within an Eclipse instance. We start from a PretriNet O design which has the basic concrete syntax to represent a PretriNet diagram. Then, the first step is to create a model to extend this O design. We open this model using the Verso editor. After this, we should load the PretriNet O design. To do this, we should right-click on the canvas, Variability, Load O design. By doing this, we can select the diagram elements that may be subject to PretriNet. In this case, PT arc, TP arc, place, and transition. After this, we're going to customize the stronger than predicates, which means to select input and output references in the class place and transition. So now that we have a good customization, we need to generate a plugin that will contain the extended editor. So right-click on the model variability, generate variability editor. So in a runtime environment, we are going to be able to use this generated editor to inject the variability in this PretriNet example. So as you can see, there's no layer, but we can activate the layer just by right-click, viewpoint selection, and variability-based PretriNet. So by doing this, the extra layer is injected, and we just activate this layer. We see that these are the presence conditions activated to these transitions and place. Right? An extra layer is injected, and we are able to attach a presence condition to this place, and we can also say that this presence condition is attached to this transition. Right? So since this is a future ID project, we're going to generate the different products. So right click on the project, feature ID, and product generation. So we're going to generate all the valid configuration. So in the folder product, we can see that we generated this 12 configuration like a running example. In the configuration 1 is activated the part B and the quality control, and this is the model that we generated using this configuration. So next, our goal is to assess whether Verso is applicable to potentially complex editors and languages built by third parties. We applied our approach to two language workbenches provided by the Sirius gallery and to the core standard graphical metamodel editor. This table summarizes the complexity of the concrete syntax and abstract syntax, the number of objects in classes, and the variability specifications. Overall, we were able to deal with large DSLs. For instance, the concrete syntax of Mozart has more than 2,000 of objects, and its metamodel has more than 150 classes. No one of the automatically adapted editors required manual adjustments, and it was very interesting that we could apply our technique to the eCore metamodel editor. Since eCore metamodels are persistent like model, this enabled the definition of language families. In this presentation, I presented our novel approach to inject variability to graphical DSLs. I implemented and evaluated a top of Eclipse using EMF and Sirius. As future work, we would like to improve comprehensibility of complex models. For instance, just display a part of the model given a certain configuration. In addition, we would like to adapt other MDE artifacts to deal with the variability, for example, textual editor, code generators, and model transformations. Besides this, we would like to provide means to check the validity of integrity constraints at family level. So thanks for watching our presentations. Any question?